Hi everyone, this is the second video for section 9.3 in which I'm going to cover a couple of examples that show some of the slightly more complicated algebraic techniques that you might need to use to set up a separable differential equation. Because the idea is pretty easy of applying integrals to both sides once it's separated. The difficulty typically comes down to making sure that you've got your sorting correct. So let's look at an example that's not in the correct form to begin with. The equation that we'll begin with is y prime plus x e to the y is equal to 0. So this doesn't start in the correct form, of course, because we don't have a derivative on one side all by itself, and we've got this junk that's added onto it, and adding is the worst possible thing you could have happen in an equation you're trying to separate. So what we're going to do is we're going to try to put it in the correct form, and then we'll try to sort the variables out once it's correct. So this will turn into y prime is equal to minus x e to the y. Now, most people feel more comfortable working with these. Instead of working in the Newton notation y prime, it's easier to see what's going on if you rewrite that as dy dx in Leibniz notation. Now what we need to do is to sort the x's and the y's out to the sides they belong on. So I can see that if I divide both sides by e to the y, I'll get dy over e to the y is equal to minus x dx. And that could be usefully rewritten as e to the minus y dy is equal to minus x dx. At this point, you're ready to go. You can integrate both sides because we have a dy side and a dx side. Everything is multiplied, and so we're set up for a separation. The integral of e to the y is minus e to the minus y, and the integral of minus x is minus 1/2 x squared plus c. And at this point, you just solve for y. E to the minus y is equal to 1/2 x squared plus c. Now, why did I write plus c instead of minus c? Because the negative of an arbitrary constant is still an arbitrary constant, so it's okay just to leave it as plus c. Now I'm going to log both sides. Minus y is equal to the natural log of 1/2 of x squared plus c. Now I can multiply through by -1 to get y is equal to the negative of the natural log of 1/2 x squared plus c. And this is the general solution to the original differential equation. The next example is an example of something called an initial value problem. So this constant over here is called an initial value. Just like in integration problems, where if I give you a single point on the graph, you can tell me what the plus c had to have been. So we're going to approach this in the same way we do the integration questions. We're going to solve the differential equation, and then when we're done, we're going to get rid of the plus c and figure out the specific number that corresponds to this initial condition by plugging these values in. You should recognize I can't do it yet because knowing a point on the function tells me nothing about a point on the derivative. So first we'll separate. Y dy is equal to x sine x dx. Now I'm prepared to integrate. So the left-hand side is easy because we get 1/2 y squared. The right-hand side we actually have to do by parts because I have a polynomial times a trig function. So I'll do the table very quickly here. x1, 0, sine of x minus the cosine of x minus the sine of x. So I get minus x cosine x plus the sine of x plus c plus minus. The point is that I have to use parts here because the integral is a polynomial times a trig function. So now what? Well, if I want to, I could completely solve this for y. But I don't need to do that in order to figure out what the c needed to have been. I can use this implicit equation to figure out the value of c because I know what the y value is supposed to be, and I know the x that corresponds to it. So from this point, I can solve the IVP by plugging in 1/2 of -1 squared is equal to minus 0 times the cosine of 0 plus the sine of 0 plus c. And what you'll end up with there is 1/2 is equal to 0 plus 0 plus c. And so there's the value of c that we wanted. So the solution to the initial value problem is 1/2 y squared minus x cosine x plus the sine of x plus 1/2. And then if I'm trying to cop out instead of do algebra, which is pretty easy in this case, but you could cop out, I guess, if I let you do that, you could just write implicitly defines the solution. And technically you would be correct, although if your professor tells you to find an explicit solution, this isn't good enough, and you'd have to keep going by multiplying by 2 and square rooting both sides. All right, so those two examples basically illustrate the core idea of working with separable differential equations. So please practice some of these. I'm going to assign a couple of word problems in here, which will require that you take a statement about the way change and a function are related and then translate it into a differential equation, so that there's a translation step, and then there's also going to be a solution step. As mathematicians, scientists, and engineers, most of the importance here is actually not in the separation step or the other techniques that are used to solve differential equations, but in writing the model down in the first place and then being able to manipulate that model to get it to match up with whatever physical situation that you're working with. You'll see a lot more of that in differential equations and in the classes that follow it. All right, see you.